Hello, Ronan. This is your Zayde, Mason. I'm here to read you Calculus for Babies. This is also for you, Leon, because I think you would enjoy this just as much. Now, I'm reading this for Ronan in particular because I've read so many books for you, Leon, and I think it's time that Ronan gets a chance to hear something. But both of you should listen to this because I think it's fun and interesting. So, let us begin. Calculus for Babies. All right. This is a ball. Now, this is a two-dimensional representation of a three-dimensional ball. And so, because we're on a flat book, all they can do is a circle that represents a ball. But it has a girth to it because you can see the shadow on the ground. And this is the shadow of the ball as represented on the ground. See that? Okay. So, the surface area of the ball is actually represented by 4 of its shadow. So the 4 times the area of its shadow represents the area of the ball. But how do we prove that? Aha! Okay, so imagine taking a piece of paper and wrapping it around the ball. Okay, that ball will be wrapped around by exactly that size of piece of paper, and you can imagine wrapping it around a ball. Okay, the paper and the ball will have exactly the same surface area, and we assume for this that the paper would actually be able to cover over to the top of it, but we're just wrapping it around the sides. Okay, question number 1 is, how tall is the paper? Well, if we consider the diameter of the ball, that is the height of the paper, because it's exactly covering the height of the ball all the way around. And then the next question is, how wide is the piece of paper that would cover this ball? And it's the same as the circumference of the ball. And the circumference is what goes around the edge of the ball as you wrap around it. What is the area of the shadow is the big question. But for that, we'll need calculus, not an ellipsis. Those are just dots saying that we're about to move on to the next bit, and this is the fun part. Okay, so we're going to take the area of the shadow, not the ball. Unfortunately, we can only, again, do this in two-dimensional representations of a three-dimensional object, and of course I'm talking to you on a flat screen, which is two-dimensional itself, so you can't really get any depth of it. But we're going to take the area of the shadow of the ball, and we're going to cut the circle of that shadow into pie slices, or like pizza slices, or whatever you like to cut into little slices. But if we take it and cut it into fourths, then we can put those fourths together and reorganize them like that. And I just want to point out that if this is the diameter of the ball, then the height of one of those is half the diameter of the ball. Okay? So, this is about half this length here is, about 1/2 of the diameter of the ball. Anyway, so if we cut it into fourths and we stack them together like that, and then we cut it instead into eighths, and then we stack it again, look how it's getting a little bit more like a rectangle. Look at that. Now, if you keep cutting it, cut it even more, it looks even more like a rectangle. That's into 16ths. Or you cut it again into 32nds. The more you cut it, the more it looks like a rectangle. We cut it into 64ths. If you cut it an infinite number of times, then you will end up with a rectangle. So we start off with that as a very rough estimate, and the smaller and smaller we make the pieces and then rearrange them again, the closer we get to eventually we end up with exactly the same area as just the shadow. And remember, that's the shadow, not the whole ball. Okay. So if you cut it into an infinite number of slices, you can rearrange it to make it look just like a rectangle. And that rectangle is exactly 1/2 the height of the diameter, and the circumference is half the circumference. So the rectangle is half the height and half the circumference of the circle. And this is of the shadow, not the whole ball. But you need 4 times that to for four shadows to meet the actual piece of paper that would have wrapped around the physical three-dimensional ball. So there you go. See? Half, 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 and you end up with the whole thing. Now you know calculus, or the fundamentals of integral calculus. Now, Sir Isaac Newton, during a pandemic, got really bored, and he invented calculus because he had nothing else to do in his house. And that's what people like him did in his time, because they didn't have television and all kinds of other electronic gadgets. They just had time on their hands. Well, maybe he had an instrument to play or books to read. I'm sure he did. But in this case, he wrote a book which described calculus, which he came up with. So this is integral calculus. We'll talk about differential calculus another time. Anyway, I hope you both have enjoyed this, Ronan and Leon. And I will try to continue on reading more books for you again soon. I love you both very much, and I will continue later on. This is your Zayde signing out for now. I will see you soon.